Now, in this lecture, we find out the area of the green shape. In the drawing, we have a circle. Inside this quarter circle, in addition, we know that the radius of this small circle is equals to the square root of 2 units in its length. And our mission is to find out the area of this green shape. So, first of all, we'll define the relevant points to this question. We'll define this point as point A. We'll define this point as point B. This is the center of the quarter circle. We'll define this point as O. We'll define this point as C. We'll define this point as D. And this is the touching point between the circle and the quarter circle. So we define this point as E. And finally, we define the center of this circle, this point as F. In the next step, we join points F and C together by a straight line. Point F is the center of the small circle. Point C is a point on the small circle itself. Therefore, FC is the radius of this small circle. And according to what is given us in the question, the radius of this small circle equals to the square root of 2 units in its length. Here we can implement all one. I'll click quickly on all one. According to all one, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle, and we have also tangent AB. This is tangent AB, that is tangent to this circle, is point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to all one. So we can implement all one in our drawing. In our drawing, we have the radius FC is drawn to point C, that is the point of tendency of tangent OD with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees. Likewise, we have here the radius FB that is drawn to point B, that is the point of tendency of tangent AO with this small circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees, according to all one, of course. In the next step, we focus on this small quadrilateral BFOC. Inside this small quadrilateral BFOC, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside quadrilateral BF or C for 360 degrees, the missing angle here must be equal to 90 degrees in its size. So quadrilateral BF or C has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral BF or C as a rectangle. And also note that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BF or C. But BF equals to the square root of 2, therefore side OC must be also equals to the square root of 2 units in its length. Likewise, according to the same rule, side FC must be equal to the opposite side BO in rectangle BF or C, but BF equals to the square root of 2 units in its length, therefore BO must be also equal to the square root of 2 units in its length. So we actually found out that quadrilateral BF or C is not a rectangle but a square because all of its sides are equal to each other. Each side equals to the square root of 2 units in its length. In the next step, we join points O and F together by a straight line. By joining points O and F, we created the right triangle OBF. We will implement the Pythagoras theorem in the right triangle OBF. In the right triangle OBF, by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle OBF is OF, therefore the square of the hypotenuse is OF squared, and it must be equal to BF squared plus BO squared. Repeat again, in the right triangle OBF, OF square must be equal to BF square plus BO square according to the Pythagoras theorem. So OF square, that is the square of the hypotenuse, must be equal to BF square. BF is square root of 2, therefore BF square is square root of 2 squared, that is 2, plus BO square. BO is also square root of 2, therefore BO square is square root of 2 squared, that is 2. In conclusion, found out that OF square equals to 2 plus 2, that is 4, so OF square equals to 4. Here we take a root out of this equation and finally we get that OF equals to the square root of 4, that is 2. Here OF equals to 2 units in its length. In the next step, I present to you a new rule and we implement a new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes for their touching point. So in the drawing we have two circles. The small circle is inside the big circle, therefore we have here an internal arch between them at point P. That is to say, the two circles are touching each other internally at point P. The center of the big circle is at point O, the center of this small circle is at point M, and the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass for point P, that is their touching point. That is to say, OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Why? Because in our drawing we have the small circle that is inside the big quarter circle, and they have an internal match between them at point E. That is to say, they are touching each other internally at point E. Whenever you have internal match between two circles, you can implement rule 9. The center, so we implement rule 9 in our drawing. The center of this quarter circle is at point O, the center of this small circle is at point F, and the straight line that connects their centers together is the straight line OF. According to rule 9, the straight line OF must pass for point E, that is their touching point. Or OFE is one straight line. OFE is one straight line. Repeat again, OFE is one straight line. Point E is the touching point. So what is the definition of line segment FE? Point F is the center of the small circle, point E is the point of the small circle itself, therefore FE is the radius of the small circle that is equals to the square root of 2 units according to what is given as the question. So we know that according to rule 9, OFE is one straight line. So OFE is also the radius of the big circle. Why? Because point O is the center of the big circle, point E is a point on the big circle itself, therefore OE is the radius of the big circle. So we define the radius of this big circle is capital R. So capital R equals to OE. So OFE is one straight line, therefore OE, the length of OE equals to OF plus FE, because it is one straight line. So OE equals to OF plus FE. So OE equals to OF, that is 2, plus FE, that is square root of 2. So in conclusion, we found out that capital R that is the radius of the big circle, equals to 2 plus square root of 2 units in its length. The radius of the big circle capital R equals to 2 plus square root of 2. So here we define the intersection point between the radius OE of the big circle to this small circle as h. We know that OFE is the radius of the big circle, therefore it is absolutely a straight line. OFE is a straight line. If OFE is a straight line, it means that HFE is also a straight line, because HFE is part of OFE. Therefore, it also must be a straight line. So HFE is a straight line that touches the small circle at points H and E. So any straight line that touches the circle at 2 points, it is defined as a chord. So HFE is a chord inside this small circle. But HFE is a chord that passes through point F, that is the center of this small circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, HE is the diameter of the circle. HE is the diameter of the small circle. Diameter of the small circle. If AG is the diameter of the circle, we know that any diameter of any circle bisects the circle into 2 equal parts, or 2 equal areas. Therefore, HE bisects the circle into 2 equal areas. That is to say, the first half this is the first half, that is actually a semicircle. And this is the second half, that is also a semicircle. So if we find out that this shape is a semicircle, in the next step I will present to you the notion of a sector. Here we have a circle, and the shape in the green color, it is defined as sector A or B. So you can see a sector as a slice of a cake. If the cake is the circle, then the sector is one slice of a cake. Okay? So this sector A or B in the green color consists of 2 legs. The first leg is AO, the second leg is BO. The 2 legs, they are both the radii of this circle, that is equal to R. Okay? And the sector exits, the legs of any sector exits from the center of the circle, that is to say from point O. From point O, and angle theta is the angle between the legs of this sector A or B. So the area of this green sector A or B equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Again, theta is the angle between the legs of this sector A or B. So pi r squared times theta over 360 degrees is the area of this green sector A or B. Okay. Our mission is to find out the area of this green shape. What is the area of this green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the big sector AOE this line above AOE is the same for a sector between sector A or B, and the squared brackets is the same for the area. So this expression means the area of sector AOE minus the area of this small semicircle the semicircle is 1/2 of this small circle. Therefore, they of course have the same radius r that equals to the square root of 2 units in its length. Minus the area of this shape B edge O. Minus the area of the orange shape B edge O. I repeat again, in total the area of this green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape B edge O. Again, the area of the green shape equals to the area of the big sector AOE minus the area of the semicircle minus the area of the orange shape B edge O. So we find out the area of each shape separately. So what is the area of the big sector AOE? The area of this big sector OAE. The area of this big sector AOE equals to pi times capital R square. This sector AOE consists of two legs. The first leg is AO and the second leg is OE. And we already found out that OE equals to capital R. It is the radius of the big circle. AO is also capital R. Why? Because point O starts from the center of the line segment AO starts from point O, that is the center of the big circle, and ends at point A, that is a point on the big circle itself. Therefore, AO is also equals to capital R, that is the radius of the big circle. Therefore, the area of the big sector AO equals to pi times capital R squared, that is the area of the big circle, times the angle between the legs of this sector over 360 degrees. Okay, So we actually have to find out the angle. This angle is very easy to see the size, to find out the size of this angle. We will focus on the right triangle OBF. In the right triangle OBF, those two sides, they are both equal to the square root of 2, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two sides that are located in front, those two angles that are located in front of those two equal sides must be equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle OBF? We have this angle that is theta plus we have this angle that is alpha plus the other angle that is alpha. Those two angles are both equal to each other. Therefore, if one angle is alpha, then the other angle must be also equal to alpha. Plus this angle that is equal to 90 degrees. So alpha plus alpha plus 90 degrees. In total, the sum of those three angles inside the right triangle OBF must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that 2 alpha equals to 90 degrees. We divide this equation by 2 and finally we get that the missing angle alpha equals to 90 degrees over 2 is equals to 45 degrees. So this is angle alpha that is equals to 45 degrees in its size. Here, write it here. Angle alpha equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees in its size. So the angle between the legs of the big sector AOE is equals to 45 degrees. This angle equals to 45 degrees. So in total, the area of the big sector AOE equals to pi times capital R squared, that is the area of the big circle, times the angle between the legs of the sector that is equals to 45 degrees over 360 degrees. So in total, the area of the big sector AOE equals to pi times capital R squared. We have already found out that capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that capital R squared will be equal to 2 plus square root of 2 squared. And we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1 over 8. So we have to divide the area of the big circle by 8. So the area of the big sector AO equals to pi, and we have here 2 plus square root of 2 squared. 2 plus square root of 2 squared according to the algebraic identity that a plus b squared equals to a squared plus b squared plus 2 times ab. So 2 plus square root of 2 squared will be equal to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2. You have to divide all by 8. So in total, the area of the big sector A or E equals to pi, and inside equals to pi, and inside the brackets we have 4 plus 2, that is 6, plus 2 times 2, that is 4. So in total, this expression will be equal to 4 times square root of 2 divided by 8. So the area of the big sector AO equals to this expression. Here we divide this both the numerator and the denominator of this expression by 2, and we get that the area of the big sector in total will be equal to pi, and inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2 divided by 8. We have to divide also the denominator 8 by 2, so 8 over 2 is 4, so in the denominator we have to only be 4. So in conclusion, we found out that the area of the big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we find out the area of the semicircle, because we have to subtract the area of the semicircle from the area of the big sector AOE in order to find out the area of the green shape. So we find out the area of this small semicircle. The area of a semicircle is the area of the circle over 2. The area of the small circle is pi r square, and if we divide it by 2, we get the area of this semicircle. So the area of the small semicircle in total will be equal to pi r square over 2. So it is pi, and r, here it is given us the question that r equals to the square root of 2, therefore r square equals to the square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of the small semicircle is equal to pi square units. And we have to subtract from the area of the big sector AOE also the area of the orange shape BHO. The area of this orange shape BHO. So what is the area of the orange shape BHO? So what is the area of the orange shape BHO? From the drawing it is very easy to see that the area of shape BHO, the orange shape BHO, equals to the area of the right triangle FBO minus the area of the small sector FBH. Repeat again. The area of the orange shape BHO equals to the area of the right triangle FBO minus the area of the small sector FBH. Again, the area of this orange shape equals to the area of this right triangle FBO minus the area of this small sector FBH. So what is the area of the right triangle FBO? The area of any right triangle equals to the base of the triangle times the height to the base over 2. The base times the height to the base over 2. So in this right triangle FBO, the base is equals to the height. They are both equal to the square root of 2 units. So the base is square root of 2, and the height is also square root of 2, and we have to divide it by 2. So square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle FBO is equals to 1 square unit. Okay. And we have to subtract from the area of this right triangle FBO the area of this small sector FBH. What is the area of this small sector FBH? The area of the small sector FBH will be equal to the area of the small circle, that is pi r squared, times the angle between the legs of this sector. This is the angle between the legs of this small sector FBH. This angle equals to 45 degrees in its side, so it is times 45 degrees over 360 degrees. So the area of the small sector FBH will be equal to pi r squared pi, and r is square root of 2, therefore r squared is square root of 2 squared, it is 2. And we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8, so we have to divide 2 pi by 8. Here we divide both the numerator and the denominator of this expression by 2. 2 pi over 2 is pi. In the denominator we have 8, so 8 over 2 is 4. So we can find out that the area of the small sector FBH is equal to pi over 4 square units. So in total we found out that the area of the orange shape B edge O is equal to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total the area of the orange shape BHO is equal to 1 minus pi over 4 square units. And our mission is to find out the area of the green shape, the area of this green shape. So the area of the green shape is equal to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So the area of the green shape equals to the area of the big sector AOE. That is actually, we will find out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. The area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the semicircle, that is equal to pi square units, which is minus pi, minus the area of the orange shape BHO, that is equal to 1 minus pi over 4 square units. So actually, the value of this expression equals to the area of the green shape. So this expression equals to pi times 3 plus 2 times square root of 2 over 4 minus pi, and here we have minus before the brackets, so we will open the brackets here and we'll get that it will be equal to minus 1 after we open the brackets, and here we have minus times minus is plus, so it is plus pi over 4. So the area of the green shape equals to pi times 3 plus 2 times square root of 2 over 4, and where minus pi plus pi over 4 is minus 3 quarter of pi minus 1. So here we multiply minus 1 by 4 and then we divide it by 4 in order to have a common factor with the other two expressions that also have 4 in their denominators. And you get that in total the area of the green shape will be equal to pi times 3 plus 2 times square root of 2 over 4 minus 3 pi. Here we multiply minus 1 by 4 and then we divide it by 4. So minus 1 times 4 is minus 4 and we have to divide all by 4. So here we open the brackets of this expression and we get that 3 times pi is 3 pi plus 2 times square root of 2 times pi is 2 times square root of 2 times pi, and we have here minus 3 pi minus 4 divided by 4. So here we have 3 pi minus 3 pi is 0, so 3 pi will get cancelled and we left only with 2 times square root of 2 times pi minus 4 over 4. So here we divide both the numerator and the denominator of this expression by 2 and we get that the area of the green shape in total will be equal to the area of the green shape equals to, here we have 2 times square root of 2 times pi over 2 is square root of 2 times pi, and we have here minus 4 over 2 is minus 2, and we have to divide the denominator of 4 also by 2, so 4 over 2 is 2. In conclusion, we found out that the area of this green shape equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers it is equals to 1.2214 square units. This is the answer to the question. I repeat again. The area of this green shape equals to the square root of 2 times pi minus 2 over 2 square units. So in terms of numbers, the area of this green shape equals to 1.2214 square units. So in the next step, I will summarize the lecture. this lecture, we found out the area of this grand shape. In the drawing, we have a circle inside this quarter circle. In addition, we know that the area of this small circle is equal to the square root of 2 units in its length. Again, our mission is to find out the area of this grand shape. So, first of all, we gave names to the relevant points of this question in this drawing. We defined this point as A, this point as B. This is the center of the quarter circle. We define the center of the quarter circle as O. We define this point as C. We define this point as D. This point is the touching point between the small circle and the big quarter circle. We define this point as C. And finally, we define the center of this small circle as F. Then we join points F and C together by a straight line. Point F is the center of the small circle, and point AC is the point on the small circle itself. Therefore, FC is the radius of this small circle that is equal to the square root of 2 units in itself. We've only given us the question. And we have here rule 1. According to rule 1, because of the fact that we have here the radius FC that is 1 to point C, that is the point of tendency obtained at OD with this circle. So whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius FB that is drawn to point B, that is the point of tendency obtained AO with this circle. Whenever your radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule 1. Okay. So, inside this quadrangle BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. That's the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees in its side. Again, in order to complete the sum of the angles inside this quadrangle FBOC to 360 degrees, the missing angle must be equal to 90 degrees in its side. So, inside quadrangle FBOC we have 4 right angles, and any quadrangle that has 4 right angles must be at least a rectangle if not a square. So, we relate to this quadrangle FOOC as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side FB equals to side OC, but FB equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, side FC must be equal to side BO. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. Okay. In the next step, we join points F and O together by a straight line. By joining points F and O, we created the right triangle FBO. In the next step, we implemented the Pythagoras theorem in this right triangle FBO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle FBO is FO, so the square of the hypotenuse is FO square, and it must be equal to BO square plus BF square. Okay, again, according to the Pythagoras theorem, in the right triangle OBF, OF square must be equal to FB square plus BO square. So here we have FB is square root of 2, therefore FB square is square root of 2 squared, that is 2, plus BO squared. BO is also square root of 2, therefore BO square is square root of 2 squared, that is 2. So in total, OF squared equals to 2 plus 2, that is 4. OF squared equals to 4, we took out all those equations, and finally found out that OF equals to the square root of 4, that is 2. Okay. We continue to focus on this right triangle FBO. It is a right triangle, it is also a isosceles triangle. That is to say, those two sides are equal to each other. Each side equals to the square root of 2, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So, and you also know that the sum of the angles in any triangle is equal to 180 degrees. And especially it's true in this right triangle BFO. So which angles we have inside the right triangle BFO? We have alpha plus alpha, that is 2 alpha plus 90 degrees equals to 180 degrees. So 2 alpha plus 90 degrees equals to 180 degrees. We subtracted 90 degrees from the equation, and we found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2, and when we found out that the missing angle alpha in this right triangle FBO equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equals to 45 degrees in inside, and this is also angle alpha that is equals to 45 degrees in inside. Okay. Then I presented to you rule 9 and we implemented rule 9 in our drawing. According to rule 9, whenever we have an internal notch between two circles, that is to say they are touching each other internally, like in this drawing, those two circles are touching each other internally at point P. Why it is internally? Because the small circle is located inside the big circle. So those two circles are touching each other internally at point P, and point O is the center of the big circle, point M is the center of the small circle, and line segment OM is a straight line that connects the joint their centers together, and according to this rule 9, the straight line OM must pass for point C. That is their touching point. Or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Because in our drawing, this small circle is located inside the big quarter circle, and they touch each other internally at point E. Whenever we have an internal notch between two circles, you can implement rule 9. Therefore, we can implement rule 9. The center of the big circle, or the big quarter circle, it is the same, is here at point O, and the center of this small circle is here at point F. And the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass for their touching point. Their touching point is here. That is, therefore, OMF, the straight line OM must pass for point E. Or OFE is one straight line. Again, OFE is one straight line. So if OFE is one straight line, it means that OFE is the radius of the big circle. Why? Because line segment OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point of the big circle itself. This is exactly the definition of a radius. Therefore, OFE or OE, it is the same. It is the radius of the big circle that we defined as capital R. And what is the length of OFE? From the moment it's very easy to see that OFE equals to OF plus FE. Again, OFE equals to OF plus FE. we already found out that OF equals to 2. And here, what is the length of FE? Point F is the center of the small circle, point E is the point of the circle itself, therefore FE is the radius of this circle is equals to the square root of 7 in its length. Okay? So, in conclusion, we found out that OE that equals to capital R, it is the radius of the big circle, equals to OF that is 2 plus FE that is square root of 2. So in total, the radius capital R of the big circle equals to 2 plus square root of 2. And OE is the radius of the big circle, therefore it is absolutely a straight line. So edge E is part of OE. If OE is a straight line, then part of edge E must be also a straight line. So edge E is a straight line that touches the small circle here at point H and here at point E. So whenever you have a straight line that touches the circle at 2 points, it will be defined as a chord. So here we have chord edge E of this small circle that passes through point F, that is the center of this small circle, and any chord that passes through the center of a circle must be the diameter of the circle. Therefore, edge E is the diameter of this small circle, and we know that the diameter of any circle bisects the circle into 2 halves. This is the first half, this is the first semicircle, and this is the other semicircle. In conclusion, we found out that this shape is the semicircle, and the semicircle and the small circle of course have the same radius, that is R is equal to the square root of 2 in its length. Then I presented to you the definition of a sector. First of all, what is a sector? A sector is a part of a circle. Here, this shape, AOB, is a sector. You can see a sector as a slice of a cake. So if the circle is itself is the cake, then the sector AOB is a slice of a cake, one slice of a cake. The sector AOB consists of 2 legs. The first leg is AO and the second leg is BO. Both of those 2 legs of sector AOB, they are the radii of the circle, that is equal to R. And the angle theta is the angle between the legs of this sector, the sector AOB. So what is the radius of this sector? Or the radius of any sector? The radius of any sector equals to pi r squared, that is the area of the circle that contains the sector, times theta over 360 degrees. Theta is the angle between the legs of this sector. So in total, the area of this sector AOB equals to pi r squared times theta over 360 degrees. Okay. Again, our mission is to find out the area of this green shape. What is the area of the green shape? From the drawings it's very easy to see that the area of the green shape equals to the area of the big sector AOE, minus the area of this small semicircle, minus the area of this orange shape, HBO. Again, the area of this green shape equals to the area of the big sector AOE, minus the area of this small semicircle, minus the area of this orange shape, HBO. Repeat again. The area of the green shape in total is equals to the area of the big sector AOE, minus the area of the small semicircle, minus the area of the orange shape, HBO. So what is the area of sector AOE? The area of sector AOE equals to the area of the circle that contains the sector. It is very easy to see that the big sector AOE is inside the big circle. Therefore, and we know that the area of the big circle equals to pi times capital R squared, because capital R is the radius of the big circle. So the area of sector AO equals to pi times capital R squared, that is the area of the big circle, times theta over 360 degrees. Theta is the angle between the legs of this sector. This angle equals to 45 degrees in its size. So theta equals to 45 degrees. This 45 degrees over 360 degrees. So the area of the big sector AO equals to pi R squared. We've already found out pi times capital R squared. We have already found out that capital R equals to 2 plus square root of 2. If capital R equals to 2 plus square root of 2, it means that capital R squared equals to 2 plus square root of 2 squared. So in total, the area of the big circle pi R squared equals to pi times 2 plus square root of 2 squared, and we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area of pi times 2 plus square root of 2 squared by 8. So the area of the big sector AO equals to, in total, to pi, and inside the brackets we have 2 plus square root of 2. 2 plus square root of 2 equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2, all divided by 8. So the area of the big sector AO equals to pi, inside the brackets we have 4 plus 2, that is 6, plus 2 times 2, that is 4, so in total this expression equals to 4 times square root of 2 over 8. Okay. In conclusion, found out that in total the area of this big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. So in the next step we found out the area of the small semicircle, the area of this small semicircle. The area of the small semicircle equals to pi r squared, that is the area of the small circle, over 2. R equals to the square root of 2 units according to what is given as the equation. Therefore, r squared equals to the square root of 2 squared, that is 2, divided by 2. 2 over 2 is 1, so in conclusion, found out that the area of the small semicircle equals to pi square units. And finally, we found out the area of this orange shape. What is the area of this orange shape? Of the orange is very easy to see that the area of the orange shape equals to the area of the right triangle FBO, this right triangle FBO, this right triangle FBO, minus the area of this small sector FBH. Again, the area of the right triangle FBO minus the area of this small sector FBH equals to the area of this orange shape. Repeat again, the area of the orange shape BHO equals to the area of the right triangle FBO minus the area of the small sector FBH. So, what is the area of the right triangle FBO? The area of any triangle equals to the base of the triangle times the height to the base over 2. The base equals to the height, they are both equal to the square root of 2 units. So, square root of 2 times square root of 2 over 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So, we can find out that the area of this right triangle FBO is equals to 1 square units. And we have to find out also the area of this small sector FBH. What is the area of the small sector FBH? The small sector FBH is part of this small circle. And the radius of this small circle equals to r equals to the square root of 2 units in its length. So the area of the small sector FBH equals to pi r squared, that is the area of the small circle, times the angle between the legs of the small sector over 360 degrees. And the next between this small sector is 45 degrees. So it is 45 degrees over 360 degrees. So pi r squared. What is r? R is square root of 2, therefore r squared is square root of 2 squared. That is 2. So this expression pi r squared equals to 2 pi, and 45 degrees over 360 degrees, it is 1 over 8. So we have to divide 2 pi by 8. Here we divided both the numerator and the denominator of this expression by 2. So 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of this small sector FBH is equal to pi over 4 square units. So the area of the orange shape BHO equals to the area of the right triangle FBO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in conclusion, we found out that the area of the orange shape BHO equals to 1 minus pi over 4 square units. Again, our mission is to find out the area of this green shape. And we know that the area of the green shape in total it is equal to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. We have already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 minus the area of the small semicircle, that is pi, minus the area of the small sector BHO, that is 1 minus pi over 4 square units. So the value of this expression, this big expression in total, will be equal to the area of the green shape. That is the area that we are looking for in this question. So the area of the green shape equals to pi times 3 plus 2 times 4 over 4, and it is minus pi, and we open the brackets here. After we open the brackets, we get that we have here minus 1, and we have here minus times minus, that is plus. So it is minus 1 plus pi over 4. So the area of the green shape equals to pi times 3 plus 2 times root of 2 over 4. Here we have minus pi plus pi over 4, that is minus 3 quarters pi minus 1. So the area of the green shape in total equals to pi times 3 plus 2 times root of 2 over 4 minus 3 pi, here, copy it from here, minus 3 pi, and here we multiplied minus 1 by 4 and then we divided by 4. So minus 1 times 4 is minus 4 divided by 4. Then we open the brackets here. Pi times 3 is 3 pi, plus 2 times root of 2 times pi is 2 times root of 2 times pi, and we have minus pi minus 4 divided by 4. Here 3 pi minus 3 pi, 3 pi minus 3 pi is 0, so 3 pi will get cancelled, and we left only with 2 times root of 2 pi minus 4 over 4. So the area of the green shape in total equals to, here we divided both the numerator and the denominator of this expression by 2. So 2 times root of 2 pi over 2 is root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator 4 also by 2. 4 over 2 is 2. So we found out that the area of the green shape in total equals to either the square root of pi times the square root of 2 minus 2 over 2, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, thank you very much.